Lab 1, Constant Velocity. Jorge Suarez, Physics 2211, Section M, Professor Alicia Munoz. Model from GlowScript and empirical model from Tracker were compared, and it was found that the baseball's motion was relatively modeled accurately in the computational model, but slightly off from the empirical evidence provided by Tracker. Newton's second law of motion. Newton's second postulate of his law of motion states the change in momentum divided by the change in time, or rate of change of momentum, is equal to the net force enacted on said object in observation. This deduction becomes incredibly useful for classical physical observation, as momentum is made up of velocity and mass of the object. Therefore, this allows for position, momentum, and velocity to be derived at multiple times from this formula. Momentum principle and update formulas, and why to use them. From Newton's second law, with some variable manipulation, final momentum and final position, and a lot more, can be determined. With a constant velocity and mass, this experiment becomes a perfect example of an observed object in motion that can be modeled easily with the momentum and position update formulas. With both of these equations, GlowScript can accurately model the updated position of our observed object every 0.01 seconds for the change in time, or delta t. Introduction. The purpose of this lab was to observe an object in motion with constant velocity and, in turn, observe Newton's second law of motion, as well as its postulates, the momentum principle, and the position update formula. The experiment observed was a baseball rolling with relatively constant velocity in order to exemplify Newton's second law of motion. Computationally modeled in GlowScript with position and velocity graphs, as well as with Tracker, which created graphs based on empirical measurement. Surroundings. For the observed experiment, the system itself under study is the baseball in constant velocity. The surroundings are everything else, including air, gravity, normal force, and friction on the ball. This is the Tracker video for the experiment. Initial conditions. Baseball is a relatively uniform in construction, but the following physical measurements were taken. Mass of baseball, 0.14 kilograms. Diameter of baseball, 0.075 meters. Initial position was 0 meters in all components, and the initial velocity was 0.474 meters per second in the x component. For initial position, the baseball started at the measured starting point, so 0 meters, and the initial velocity was determined by taking the position at t equals 0.2 seconds from Tracker and dividing by the change in time, which gave approximately 0.474 meters per second in the positive x direction, as the initial velocity of the baseball. These were the position curves plotted over time in meters and seconds for both the computational model in GlowScript as well as our Tracker data. Computational model components. The most important components of the computational model started first with the initialized mass 0.145 kilograms of the baseball in line 31. The initial position 0 meters and velocity 0.474 meters per second were then entered in lines 34 and 35. Initial time 0 seconds as well as change in time step 0.01 seconds or delta t were initialized in lines 38 and 39. The model then truly computes the motion in the while loop from t equals 0 to t equals 2.26 seconds, lines 48 to 62. Where in lines 57, the velocity update formula, and in line 59, the position update formula, both derived from Newton's second law, are computed every 0.01 seconds for the baseball versus empirical data. The position curve of the baseball given by Tracker data is much more concave than GlowScript computational model. This is due to the Tracker data following the actual position of the baseball versus the computational model modeling constant velocity in perfect conditions. There's also likely differences due to human error and unforeseen variables in trial. Sources of error. Some possible sources for the difference between our computational model include the shape of the baseball's true path, and the frictional forces. Baseballs have sewn panels. These panels have curved edges due to the string holding the baseball together. When rolling over these edges, the ball does not have uniform shape, thus causing the ball to lose momentum and velocity. Furthermore, the baseball also changes path due to these seams, thus some y component is there that is not measured in the lab, decreasing the velocity in the positive direction. Finally, frictional force against the path of the baseball exists as the ball is rolling across the ground, a surface. The baseball was rolled across tile in order to reduce the frictional force as much as possible, but in a real-world application, there will always be some momentum lost. Discussion. The lab ultimately exemplified Newton's second law of motion by observing an object's motion with constant velocity. With a constant velocity, the baseball does not accelerate, therefore allowing for calculations with the position update formula to be made, as this equation is originally derived algebraically from Newton's second law. With constant velocity in motion, the ball continues to roll, which is the premise of Newton's second law. There's no net force interacting from the surroundings on the system or the baseball, therefore the baseball will remain in motion with constant velocity. In the results, it was found that the Tracker data showed a concave change in position over time, signifying that the velocity was not perfectly constant. This is most likely due to the seams of the baseball changing the baseball's path. Frictional force acting upon the ball and human error of placing the tracking squares and tracker. Ultimately, both curves started and ended at similar positions. Therefore, though there were differences in the data, the overall principle was supported. What if and what does it mean? What if the orientation of the axis or axes were different in tracker? The direction of the velocity would be in different directions, hopefully still parallel/perpendicular to the ball, which would cause the velocity to be in negative x direction instead. If the axes were offset, there would be x and y components to the velocity, making the lab more complicated, but constant velocity and uniform motion would still be observed. Is it possible for you to say how many pushes and pulls, i.e. how many forces, are added together to give zero net force in the case that you observed? Since the experiment took place on Earth, gravitational force was exerted on the ball downwards. Since the ball didn't break through the ground, normal force of the ground must have pushed upwards in the exact opposite direction with equal magnitude, thus conserving a net force of zero. Frictional force was also applied to the ball, but this is a source of error rather than empirical observation for the experiment.